Imagine you're the captain of a multi-million-dollar oil tanker.
Right.
And you are navigating the English Channel in this dense, just totally blinding fog.
Terrifying.
Yeah. So you look down at your digital map, and the glowing blue dot shows your vessel perfectly centered in the designated shipping lane. You feel safe.
Because why wouldn't you?
Exactly. But then you look out the bridge window, and the fog breaks for just a second, and you see you are like 500 yards off course, heading straight for a jagged reef.
Oh, wow.
Yeah, and no alarms are sounding. Your state-of-the-art navigation system isn't malfunctioning. It is actively lying to you.
And honestly, that is the terrifying reality of modern maritime navigation right now. We place this blind faith in invisible digital signals, and we just assume they're the absolute truth.
Which they aren't. So, welcome to this custom-tailored deep dive. Our mission today is to shortcut your way to being fully informed on a vulnerability in global navigation that is just, it's honestly chilling.
It really is.
And we are pulling all our insights from a primary source today. It's a highly detailed article published in the Deep Draft.
Which is a really respected professional maritime analysis platform.
Yeah, and this wasn't written by, some armchair theorist. It comes from Captain Raghu Sharma, who is a serving master mariner.
And I think the timing of his analysis is just so critical here. The context surrounding this issue makes it far more than just an academic exercise.
Right. Let's set the scene for you real quick to give you that context. It is March 2026. The geopolitical backdrop is incredibly tense.
To put it mildly.
Yeah. Just glancing at the Livewire section of our source material, the headlines are flashing red. We're looking at reports of U.S. strikes on Karg Island military targets.
Right.
Destroyed Iranian mine layers. Triple ship strikes off the UAE. And Brent crude oil has rebounded to, $114 a barrel?
Yeah, 114. It's massive.
So the world's waterways currently look like a total powder keg.
They do. And in that highly volatile environment, ship captains are navigating vessels that literally carry the lifeblood of the global economy.
Yeah.
And they're going through these incredibly dangerous choke points. The threat of physical violence is, it's palpable.
But the real danger, the one that actually keeps maritime security experts awake at night, might not be visible at all.
No, it's not.
We aren't talking about a physical naval blockade or, explosive drones here. We are talking about invisible fabricated signals.
Exactly.
Today's topic is GPS spoofing. We are looking at exactly what happens when the satellite data we rely on every single day gets hijacked.
And to fully grasp the implications of that for global shipping, you really first have to understand the sheer delicacy of the GPS system itself.
Yeah.
It's a modern marvel, obviously, but its foundational architecture is surprisingly fragile.
Okay, let's unpack this, because before we get to the giant cargo ships crashing in the English Channel, let's look at the mechanics of how GPS actually works. According to the text, a GPS receiver figures out its position by calculating its distance from several different satellites in orbit, all at the exact same time.
Right.
Which sounds simple enough, but the text points out this massive logistical hurdle. All of those civilian GPS satellites broadcast their signals on the exact same frequency.
Yeah, which naturally creates this completely chaotic environment for any receiver on the ground.
I'd imagine.
Right. If every single satellite in space is shouting its location down to Earth on the exact same radio frequency, a ship's navigation antenna needs a way to filter that noise and figure out who is speaking.
And the text explains that they solve this using something called a pseudorandom noise code, or a PRN code.
Exactly.
It kind of acts as a digital signature. Each satellite broadcasts its location, the exact time, and its unique PRN code.
And that PRN code is the linchpin of the entire system's trust.
Right.
And what a spoofer does is systematically dismantle that trust. The text breaks the spoofing process down into two distinct phases. Phase 1 is basically the setup. The attacker needs to figure out exactly which GPS satellites are currently in the sky above their target.
Because satellite orbits are public knowledge, right? Anyone with an internet connection can just look up a digital timetable and see exactly where a satellite is supposed to be at any given millisecond.
Yeah, exactly. And that public visibility is the first huge vulnerability.
Wow.
So the spoofer identifies the nearby satellites and then uses software to mathematically fabricate the unique PRN code for each one.
So they just forge the signature?
Yes. Once they forge those digital signatures, they start broadcasting these really faint radio signals carrying those fabricated codes all at once.
Why faint, though?
Because your GPS receiver is designed to listen for incredibly weak signals traveling thousands of miles from space.
Oh, right.
So it registers this localized weak transmission as genuine.
Okay, so it's like someone standing in a crowded room, perfectly mimicking the voice of your friend, but whispering just loud enough for you to hear over the crowd.
That is a perfect analogy.
Like, your brain latches onto the familiar voice, not realizing the person speaking is actually right behind you, not across the room.
Exactly. That whisper analogy captures the stealth of Phase 1 perfectly. But Phase 2 is where the actual hijacking occurs.
Right.
Captain Sharma refers to this as the delicate art of the drag-off.
The drag off. See, if I'm the hacker, my instinct is just to blast my fake signal at maximum power to drown out the real satellites instantly.
Sure.
Like, why not just brute force it and take over the receiver right away?
Well, if you do that, the ship's software flags it immediately.
Hmm.
An abrupt spike in signal power triggers an anomaly alarm.
Oh, because that doesn't make sense physically.
Right. The system knows something is physically impossible about a satellite suddenly becoming 10 times louder.
Yeah, that makes sense.
That's why it has to be this slow seduction of the receiver's antenna. The spoofer gradually increases the power of their false signals.
Very slowly.
Very slowly, carefully matching the trajectory and timing of the real ones until the receiver's internal tracking loops literally lock onto the fake signal instead of the real one.
So it's less like a sudden kidnapping and more like slowly adjusting the thermostat in a room.
Yes.
You turn it down 1 degree at a time, and the person sitting there doesn't realize they are freezing until it's too late.
A very apt comparison. And once that lock is achieved, the spoofer has complete control over the mathematical reality of the receiver.
That is wild.
The text notes that the operator can then manipulate the underlying algorithms to shift the target's perceived location.
How do they do that?
They feed false data that actually moves the coordinates of the Earth's center, or alters the Earth's radius in the calculation, or even shifts the simulated position of the GPS satellite itself.
Man, you hear about a drag-off process, fabricating satellite algorithms, manipulating the Earth's radius, and your mind immediately goes to James Bond villains,
Go ahead.
sitting in billion-dollar underground bunkers. But the most terrifying part of this entire report is the price tag. We aren't talking about billions of dollars here.
Not at all. The barrier to entry is almost non-existent now. The democratization of this disruption is the core of the modern threat.
Yeah, the author explicitly states that GPS spoofing can be done by rogue nation-states, sure, but it can also be done by petty criminals.
Right.
The text even specifically says even a mischievous teenager.
Which is terrifying.
To pull off a drag-off, all it takes is a high-end laptop, a device called a GPS SDR SIM to generate the signal data streams, and a software-defined radio platform, or SDR, to transmit the radio frequencies.
And that software-defined radio is the technological leap that made all this accessible.
Really?
Yeah, because in the past, generating specific radio frequencies required custom-built, highly expensive physical hardware.
Like actual big machines.
Exactly. Copper and silicon perfectly tuned to a task. An SDR replaces all that expensive hardware with cheap downloadable software. You pair it with a generic antenna, and your laptop can suddenly broadcast on almost any frequency.
And the software needed to run the spoofing algorithms, it's freely available on the internet. You can literally just download the tools to hijack a satellite signal.
It's all right there.
But let me pause here and ask a foundational question. Is this just the same thing as when I'm driving downtown, my GPS drops out among the skyscrapers, and I get a signal jammed warning?
Well, no. Jamming and spoofing are frequently confused, but our text highlights a critical distinction in how they operate.
Okay, what's the difference?
Jamming is a brute force denial of service. It involves blasting random radio noise across the GPS frequency so that the receiver is completely deafened. If spoofing is whispering a lie in your ear, jamming is just standing next to you and screaming at the top of their lungs so you cannot hear the person across the room.
Okay, so with jamming, I at least know I am being attacked.
Right.
My navigation screen throws up an error message, and I know I have to pull over and look at a physical map.
Exactly. Spoofing removes that awareness entirely. The text emphasizes that the user may never realize their equipment has been compromised.
Because there are no error messages?
None. The blue dot stays perfectly blue, it just leads you off a cliff.
Here's where it gets really interesting. The text provides the surreal, real-world example of the stealth in action.
Oh, the Moscow anomaly.
Yes. It references findings by researchers, including Todd Humphreys from the University of Texas at Austin, who tracked strange anomalies occurring in central Moscow.
Right.
Over the course of a year, civilian phone apps in the center of the city started going completely haywire.
Yeah.
But the sheer scale of this massive spoofing operation wasn't fully grasped by the public until people started trying to play the mobile game Pokemon Go.
It is just a profound collision of global electronic warfare and augmented reality gaming.
Players walking right next to the Kremlin suddenly found their digital avatars sprinting 32 kilometers away to Vankovo Airport.
Which is quite the hike.
Right. The fake signal was grabbing any civilian receiver in the area, phones, fitness trackers, car navigation, and violently dragging them miles outside the city center.
And our source notes that researchers attribute this to Russia experimenting with electronic warfare to defend against NATO-guided bombs, missiles, and drones.
Right.
Because those automated weapons rely heavily on GPS navigation. So, successfully spoofing the airspace over the Kremlin theoretically protects the area. The weapons simply believe they are at an airport 32 kilometers away.
Now, just to be incredibly clear to you listening right now, we are completely impartial here.
Right, exactly. We're not taking sides.
Yeah, we aren't endorsing any NATO or Russian military doctrines or geopolitical strategies.
No, not at all.
We are strictly looking at this through the impartial lens of our source material to highlight the sheer citywide scale that this spoofing technology has already achieved.
Exactly. It just perfectly illustrates the scale.
But that transition from the streets of Moscow to the world's oceans is where the math gets deadly. Because moving a Pokemon player 32 kilometers is a nuisance. You miss out on catching a rare character. But moving a massive, fully loaded cargo ship that same distance, you are looking at an environmental and economic catastrophe.
And this brings us to the operational reality on the bridge of a modern vessel. Navigators today have fundamentally changed how they chart a course.
How so?
Well, the text points out that modern shipping relies heavily on automated GPS position fixing integrated into a system called ECDI.
ECDI, which stands for Electronic Chart Display and Information System, right?
Yes.
It's essentially the giant, hyper-accurate digital map that serves as the central brain of the ship's bridge.
But it's far more than just a map. ECDIS integrates the GPS position, the ship's speed, its heading, and radar data to project exactly where the ship is and where it will be in 10 minutes.
Okay.
If the officers rely solely on that integrated GPS feed for their position plotting, they stop looking out the window. They trust the screen.
And the threat to that screen isn't equal across the entire ocean.
No, it's not.
The author notes that spoofing signals normally originate from land-based stations because the physics of radio waves require relatively close proximity and line of sight.
Right.
So while a rogue vessel mid-ocean could theoretically broadcast a spoofing signal, the primary danger zones are really coastal waters.
And coastal waters are already the most complex environments to navigate in the first place.
Yeah.
You have land masses, shallow depths, and high traffic density.
The author paints a terrifying scenario, specifically calling out the English Channel.
Yeah.
Imagine congested waters, terrible weather, and low visibility. If a ship's GPS is dragged off in the English Channel, the author bluntly states it would cause great confusion and likely collisions.
The psychology of the navigator in that moment is what makes the attack so effective. The text highlights a truly insidious aspect of how the spoofing manifests depending on the distance.
What do you mean?
Well, if the spoofed position is very close to the ship's actual position, like a subtle drag-off of just a few hundred yards, it can remain completely unnoticed for a long time. The crew looks at the ECDIS, sees they are perfectly centered in the shipping lane, and feels no need to verify. They're actually drifting toward a sandbank, but the illusion holds.
But by the time the hull scrapes the bottom, it's too late to correct.
Exactly. Conversely, if the spoofer attempts a massive jump like that 32-kilometer relocation we saw in Moscow, the crew will notice it immediately.
Sure, because it's so drastic.
But as the text notes, detection does not equal safety. A sudden, massive jump causes instant, dangerous confusion on the bridge.
Oh, I bet.
The ECDIS alarms start blaring because the system's logic detects an impossible leap in physical space.
Right.
The primary and secondary navigation systems might start fighting each other, displaying contradictory information. In a narrow, heavily trafficked channel, that level of panic and confusion is just deadly.
So what does this all mean? We have a situation where the high-tech systems we built to keep us safe are being weaponized against us.
Yeah.
The seas, especially in this 2026 timeframe, are incredibly hostile. How do mariners actually survive this?
Survival requires a layered defense. You have to combine the oldest maritime traditions with the newest software engineering.
And the U.S. Coast Guard actually issued formal advice on this. And the profound irony of their solution is just staggering to me.
It really is.
To defeat a 21st century, highly sophisticated cyber attack involving software-defined radios and fabricated satellite algorithms,
Yeah.
modern mariners are being told to use celestial navigation for ocean passages.
Reverting to the stars.
I just love that imagery.
A hacker sitting in a basement with a laptop cannot spoof the physical position of the North Star.
The idea of a modern captain standing on a bridge filled with millions of dollars of touchscreens, pulling out a brass sextant to outsmart a cyber attack is incredible.
It is a very pragmatic acknowledgement of vulnerability. However, celestial navigation is only useful for deep ocean passages where you have time and open horizons.
Good point.
For those highly vulnerable coastal waters we talked about, the defense strategies have to be immediate and tactical.
Yeah, and the author lists specific, old-school techniques for coastal navigation when spoofing is suspected. The core theme seems to be relentless cross-checking.
Exactly. You cannot trust a single source of data. The text outlines using parallel indexing.
Which is what?
It involves using fixed radar echoes from the shoreline to maintain a safe distance, regardless of what the GPS says.
Okay, that makes sense.
They also advise using radar overlays on the electronic charts, checking echo sounder references for depth, and taking good old-fashioned visual fixes using a compass and landmarks.
Right, because if the GPS says you are a mile offshore, but your radar clearly shows the coastline is only half a mile away, you have a critical discrepancy.
Huge discrepancy.
But you would think the ship's computer would just catch that discrepancy itself. Like, doesn't the ECDIS system have an alarm that alerts the crew if there's a difference between the primary and secondary systems?
It does, but there's a massive flaw in that logic. If a ship has two independent GPS receivers, and the spoofer's radio signal blankets the entire vessel, both receivers get dragged off at the exact same time.
Oh.
So the ECDIS checks receiver A against receiver B, sees they match, and assumes everything is fine. The alarm never sounds.
Man, which completely underscores why verifying against non-GPS methods like radar or visual sites is totally non-negotiable.
Right. But the maritime industry isn't just throwing its hands up and relying solely on radar and sextants. The text outlines 4 robust software and hardware-side preventions designed to harden the ships against these attacks.
The hardware arms race is fascinating here. Let's walk through those 4 solutions the author proposes. Number 1 is adding dedicated sensors or blockers.
Yeah, these are specialized antenna systems designed specifically to analyze the incoming radio frequency environment.
What are they looking for?
They look for the telltale characteristics of interference, jamming, and spoofing signals, like that slow, unnatural increase in power during a drag-off. When they detect an anomaly, they provide a local alert to the bridge, communicate the threat to remote monitoring centers ashore, and collect the forensic data of the attack.
Very cool. So number 2 involves extending data spoofing whitelists directly to those sensors.
Yes.
Because the government reference software used to track GPS reliability already uses digital whitelists, which are basically VIP lists of mathematically authenticated signals.
Exactly.
And the text argues that this whitelist architecture needs to be implemented directly into the commercial ship's sensors to filter out the fabricated PRN codes.
Right. And then number 3 is perhaps the most systemic fix of all of them, which is utilizing modernized GPS signal types.
Why is that so important?
This is critical to understand. The legacy civilian signals, known as L1 signals, were designed literally decades ago.
Right.
They are unencrypted, openly documented, and fundamentally weak against modern interference. The text strongly advises the industry to leverage modernized civil GPS signals like L2 and L5.
Because they're stronger.
Much stronger. These newer signals have a much more robust architecture, they broadcast on different frequencies, and they are significantly more resistant to spoofing.
Okay, and finally, number 4, reducing latency. The author explains that latency is the lag time between when a receiver is misled by an attack and when the system actually recognizes the corruption.
Right.
If that lag time is too long, the corrupted location data gets handed over to the ship's backup devices, infecting the autopilot and the ECDIS.
So the goal is to reduce that latency so the system spots the lie and severs the connection before the fake data poisons the rest of the bridge.
It's a constant technological race, isn't it?
It really is. High-end receivers with advanced spoofing detection offer a strong defense today. But as open-source software and SDR hardware inevitably become more sophisticated, the attacks will become harder to detect.
It's basically an invisible war being fought over the very coordinates of reality. To bring our deep dive to a close today, the threat of GPS spoofing isn't a theoretical military exercise anymore. It is a highly accessible, stealthy weapon capable of silently dragging a massive cargo ship into a catastrophic collision.
Absolutely.
As Captain Sharma so perfectly summarized in his article, and I have to share his pun with you, ship happens.
It certainly does.
The ultimate defense, whether you are steering a supertanker through the English Channel or simply navigating the complexities of the modern world, is relentless cross-checking. You cannot let one single screen dictate your reality.
So true. The foundational systems we rely on are shifting beneath us. We've explored how a core technology like GPS, which synchronizes our financial markets, our power grids, and our global supply chains, can be gently dragged off course by someone with a laptop and a downloaded script.
Right.
It forces seasoned ship captains to look away from their screens and back up at the stars for the absolute truth. It leaves you with a profound question. What other invisible digital signals are you blindly trusting to guide your daily life? And how far off course would you have to be dragged before you finally looked up to check your surroundings?
A brilliant thought to leave you with. Thank you for joining us on this deep dive. Stay vigilant, always verify your coordinates, and stay curious.